So now let's explain the code. I wrote a hands-on exam tutorial for the 1D burgers equation. And in this example, firstly, you need to import some important Python packages. And we set a seed, random seed, to make sure the different people and around different times can have the same solution. So at the beginning, you can define the FNO model. It requires you to define two classes. The first one is a special convolution for 1D, and it actually have three arguments: the input channel, the output channel, and the number of modes. Number of modes means number of Fourier modes that you want to keep to multiply. And the second class is Fourier Neural Operator 1D. So let's go to the Fourier Neural Operator 1D at first. So in this example, at first you need to define the number of modes you want to keep. The number of modes is like how many low frequency information you want to keep. And then the width is actually the hidden number of channel, the hidden channel number. FC0 is actually the first MLP to lift your channel from 2. 2 is because you have your initial condition and also your spatial coordinates. So here you lift your input channel from 2 to the number of weights. It's actually a hidden channel. After that, we define some convolution operation. This is actually a spectral convolution. They will use a same number of weights to make it a standard operation. And the W0 is actually the 1-by-1 convolution. So for 1-by-1 convolution, we'll keep using the same number of input channel and output channel to make sure your input data and your output for this 1-by-1 convolution will be the same. And after that, because we will have this tensor that has the weights number of channel, so we will change it to increase it to 128 and decrease it to 1. But you can also do it directly from 1. And this is actually some trial and error, and you can find increased number of fully connected layer, the performance can be better. So let's go to the forward parts. For the forward part, the first thing is we need to lift the channel from 2 to the number of widths. So here is 64. So the FC, the input X, the dimension is a batch number and the number of spatial and number of channel. And we change it to this, which we increase the number of channel to here. And we change the number of the dimension of the axis of channel and also the X. After that, the stage 2 is actually to do some integral like operator. And you will have 4 blocks: the first block and the second block and the third block and fourth block. So you can do that. You can see the input and output will always the same. It is a batch, and C is actually the width and the number of resolution. So in stage 3, we will try to put the channel back to 1 and do the permute to change the axis. And after that, you can do the F1, a fully connected MLP, and you can increase the number of channel to 128, and eventually decrease it to 1 because we only want the solution at one time step. So after defining this model, okay, we need to go to what is a spectral convolution 1D. Spectral convolution 1D, let's go to the forward part. Firstly, we compute the Fourier coefficient. This is a Fourier coefficient. And the input X is this batch and C input, the channel number, input channel number, and also the spatial resolution. So here we decrease it to from 200, 180, 128 to 68, 65 actually, 65. And we'll multiply the relevant Fourier modes. We do a linear transformation at here, linear transformation. This is actually a complex multiplication. And you can see some documents at here, at least at here. And after that, we need to do the inverse transformation of Fourier transformation so we can return to the physical space. Then eventually, the input will be exactly the same of the output will be exactly the same of the input because C input channel and output channel is the same. After defining this channel, and we need to, if we want to train our model, we need to have some configuration. The first configuration is like we need to know the data. You need to download the data from here, from this link, and you need to create a new data set at this folder, for your new FNO1D. Put a data set at here. So S sub equal to 8 means the downsample rate or spatial dimension because the original resolution is very high, it's more than 8,000. And for the training, we only use a first 1,000 trajectory to train the model and test the last 200 trajectories. There are some training parameters, and the number of epochs is 500, and you can set the different batch size and some parameter for the optimizer, and we use a learning rate for this, and the number of modes. So here we keep the number of modes as 16, and at most it can be for n divided 2 plus 1. Number of hidden channel is 64. This is very important. You can try for each different one. And we will save our model to this place. So here's, we need to do prepare our data set, especially the data loader. We will load our raw data using load mat, and we will call the prepare data function and to get the training loader and test loader. So at here, we basically extract the initial condition and the final solution, and we do the downsample. We can get X data and Y data. And after that, we split the data into this training and testing. So this is the first 1,000 data, and this is the last 200 data. And here is prepare the grid and the coordinates. The spatial domain is from 0 to 1, and this is the original resolution. And here we do the downsample similarly to this one. And we can change it to the tensor. And here we concatenate the training data. The training data here has the shape of a number of samples. And here is the number of your spatial resolution. Here is 1. Because this is a channel. The first channel is only 1. And here is a grade. Eventually the grade will be created as a shape like this. No. This is a repeater operation. So eventually you can find we can concatenate and have this tensor. This tensor has 2 channels, and we will create a data loader for that. The data loader, and here you can define the batch size, and this is a data loader from tensor. And here it doesn't have any like shuffle operation. After you prepare this channel, you can find the raw data. After we do the downsample, the raw data is we can have 2,000 148 trajectories, and for each trajectory, it has a 1224 resolution, and this is a spatial resolution. And we try to next we can do the model training. For the model training, we need to firstly define the model and put the model in CUDA, and we will use an Adam optimizer, and we will use a stepwise learning rate decay. So in this paper, they use actually a LP loss. It's actually a relative loss, but we use a mean square error. I think that it's kind of similar. It doesn't change the model, doesn't change the performance very much. So here we use two lists to save the loss, so we can print the loss history. And we start the training, and for each one we have X and Y. X is actually the initial condition, Y is a ground truth model prediction. It's actually a solution at one time step. And we do the training and do the loss function, gradient descent, and we update the learning rate. And for each epoch, we do the evaluation, and we put the loss history, like test loss, in this list. And we print some epochs. So you can see if we have 500 epochs, so the error can be reached to a very low number. So here you can plot the loss history for training and testing. You can see this is training loss and this is a test loss. It's very low. After we train the model, and we also save the model, so we can do the evaluation. One special evaluation for this model is that you can actually test the model on different low resolution. It can be 64, 220, 56, or 1024. So here, this is you can do the for loop for each test resolution, and this is a downsample rate. And based on this downsample rate, we can prepare our test data loader. We can do the test, and here I only do the visualization for the last sample, last batch sample. And you can see this is a low resolution inference prediction, and this is a higher, and this is a highest resolution prediction. So from this, you can also check the code at this website. Yeah, we actually define the model and do the configuration and prepare the training data and train the model and do the evaluation. But note that in this example, we only learn the operator from initial condition to a certain time step solution. And in the future, we will do the autoregressive training for more temporal dynamics, and also we'll consider the two-dimensional space, two-dimensional data, and also three-dimensional data. Thank you. Thanks for watching this video.